For centuries, humanity has peered into the cosmos, searching for answers about the origins of the universe. Black holes, regions of space so dense that even light cannot escape, have long been a subject of mystery. Until now, every black hole ever observed was already fully formed, devouring matter and warping space-time. But what if we could witness the moment of their birth? In the year 2025, a historic breakthrough shook the scientific community to its core. The James Webb Space Telescope, JWST, the most advanced observatory ever launched, captured an unprecedented cosmic event, the birth of a black hole. Never before had scientists witnessed the very moment a singularity came into existence. This discovery would challenge fundamental theories of astrophysics, reshape our understanding of gravity, and open new frontiers in the study of the universe. This is the story of how the James Webb Space Telescope uncovered the emergence of darkness itself. Orbiting 1.5 million kilometers from Earth at the second Lagrange point, L2, the James Webb Space Telescope had already rewritten the history of astronomy. Its powerful infrared vision had pierced through cosmic dust, revealing the earliest galaxies formed after the Big Bang and detecting atmospheres of exoplanets with unprecedented detail. But no one could have anticipated what it would capture on the night of August 7th, 2025. Astronomers at NASA's Goddard Space Flight Center were analyzing deep-field images of a distant region in the Boötes Void, a massive empty space spanning 330 million light-years across. The JWST was studying a seemingly ordinary cloud of collapsing gas when something extraordinary happened. A point of infinite darkness began to form, a disturbance so profound that it bent the very fabric of space-time in real time. For the first time in human history, a black hole was being born before our eyes. The event originated from a massive star, a hypergiant over 50 times the mass of our Sun, undergoing its final moments. As it collapsed, its core could no longer sustain nuclear fusion, triggering a cataclysmic hypernova, a stellar explosion many times more powerful than a supernova. However, something was different. Instead of dispersing its outer layers and leaving behind a neutron star, the core's density increased exponentially, forming a singularity in real time. Scientists had theorized that black holes formed over extended periods, their presence inferred by the gravitational influence they exert on nearby celestial objects. But here, JWST was providing visual and infrared evidence of a black hole forming in real time, consuming the very light around it. Within seconds, the surrounding region of space bent as if being sucked into an unseen abyss. The moment of singularity, the point at which matter collapsed infinitely upon itself, had begun. As the data streamed back to Earth, observatories worldwide were alerted. Harvard-Smithsonian Center for Astrophysics, MIT, Caltech, and the European Southern Observatory, ESO, scrambled to confirm the findings. Some scientists initially dismissed it as an illusion caused by gravitational lensing. But as JWST continued to collect images and infrared spectroscopy data, the truth became undeniable. The birth of a black hole was no longer just a theory. It was now observable science. Astrophysicist Dr. Eleanor Vasquez, one of the leading experts in black hole physics at NASA, couldn't contain her excitement. For years, we've studied black holes as relics of dead stars, but we've never actually seen one forming. This is the first time in history we are witnessing the exact moment a singularity is born. The newly forming black hole, which scientists quickly named Charybdis 1, was absorbing matter at an unprecedented rate. As surrounding gas spiraled inward, it created a powerful accretion disk, glowing with intense X-rays and infrared radiation. But JWST's near-infrared camera, an IR-CAM, detected something even more astonishing, a gravitational wave ripple propagating outward. This meant that the formation of Charybdis 1 was so violent that it sent shock waves through space-time itself. The event was relayed to LIGO, Laser Interferometer Gravitational Wave Observatory, which confirmed a never-before-seen signature of a birth wave, a gravitational signal distinct from those detected in black hole mergers. This revelation suggested that black holes might not simply appear, but undergo a process of formation that emits detectable waves. As more data poured in, theoretical physicists struggled to explain what they were seeing. Some aspects of Charybdis 1's formation contradicted the conventional Einsteinian predictions of general relativity. One anomaly was its event horizon, the boundary beyond which nothing can escape. Instead of forming instantaneously, it appeared to fluctuate before stabilizing, a phenomenon that had only been speculated in quantum gravity theories. Could this be evidence of a quantum bridge between relativity and quantum mechanics? Meanwhile, the accretion disk of a newborn black hole emitted powerful relativistic jets, streams of particles traveling at nearly the speed of light. But these jets showed an unusual spiral polarization, hinting at an unknown interaction between the singularity and space-time. The laws of physics were being rewritten before humanity's eyes. News of the discovery spread rapidly. From NASA headquarters to the halls of CERN, discussions about the implications of Charybdis 1 dominated scientific forums. Universities introduced new research programs dedicated to studying the event, and the James Webb Space Telescope was hailed as the most transformative scientific instrument of the 21st century. Even the philosophical implications were staggering. The birth of a black hole, an event of infinite collapse, raised questions about the nature of reality itself. If black holes were the seeds of new universes, as some physicists hypothesized, could JWST have just witnessed the birth of an entirely new cosmos? Charybdis 1 was just the beginning. With a newfound ability to observe black hole formation, astronomers launched Project Singularity, a collaborative effort to identify and monitor more forming black holes across the cosmos. JWST, alongside future observatories like the Einstein Telescope and LUVOIR, was tasked with scanning deep space for similar phenomena. The goal? To understand whether black hole births were rare cosmic accidents or a fundamental process shaping the universe. The discovery of Charybdis 1 reshaped astrophysics forever, proving that even in the darkest corners of space, there was still so much to learn. The detection of the first ever emerging black hole changed everything. It proved that black holes were not just the remnants of dead stars, but dynamic, evolving entities. It provided the first real-time evidence of singularity formation and hinted at new physics beyond Einstein's theories. As humanity continued to peer into the abyss, one truth remained clear. The universe still holds secrets we are only beginning to uncover. The discovery of Charybdis 1, the first ever observed forming black hole, had sent shockwaves through the scientific world. Physicists, astronomers, and theorists scrambled to make sense of the implications. At NASA's Goddard Space Flight Center, Dr. Eleanor Vasquez and her team analyzed the newest data streams from the James Webb Space Telescope, JWST. Despite initial skepticism, other space observatories, including the Chandra X-ray Observatory, the Very Large Telescope, VLT, and the Event Horizon Telescope, EHD, began confirming JWST's findings. The black hole was still in its early formation, but something strange was happening. It wasn't behaving like any known black hole. While it continued to absorb gas and matter at an immense rate, some of its characteristics were unusual. Its gravitational effects fluctuated erratically, almost as if the event horizon was unstable. More alarmingly, new gravitational waves rippled outward, unlike anything previously recorded. Could this mean Charybdis 1 was a new kind of black hole? The world's leading black hole expert, Dr. Amir Patel from Caltech, reviewed the incoming data and made a startling hypothesis. Unlike traditional stellar mass black holes, which form after a supernova, Charybdis 1 seemed to be undergoing a slow collapse, its event horizon forming in stages. Patel proposed that this could be the first evidence of a delayed singularity, a black hole whose collapse didn't happen instantaneously, but instead unfolded over time. This defied Einstein's general theory of relativity, which predicted that a collapsing star should transition into a black hole almost immediately. The phenomenon also hinted at something even more profound: quantum effects at play within a macroscopic singularity. Could it be that black holes weren't just infinitely dense points, but instead complex structures governed by yet unknown forces? 3 weeks after the discovery, the LIGO and Virgo gravitational wave observatories detected an unexpected signal. Instead of the usual waves caused by black hole mergers or neutron star collisions, this signal pulsed in a regular interval, like a cosmic heartbeat. Dr. Vasquez and her team cross-referenced the data with JWST's observations. The pulses were originating from Charybdis 1 itself. No known black hole had ever exhibited this kind of rhythmic emission. Could this be an indication of quantum fluctuations within the event horizon? Or worse, could Charybdis 1 be unstable? NASA called an emergency summit of the world's top astrophysicists. The data presented was clear: Charybdis 1 was violating known physics. Instead of a static event horizon, the black hole's boundary appeared to oscillate, expanding and contracting slightly. Some theorists suggested that this could mean: 1. The event horizon wasn't fully formed yet. Charybdis 1 was still in a transitional phase. 2. Charybdis 1 could be a new type of semi-black hole, one that blurred the line between relativity and quantum mechanics. 3. An unknown force or structure was preventing full collapse, meaning the black hole might not be a singularity at all. If the third possibility were true, it would mean that the very foundation of black hole physics was flawed. To confirm the nature of Charybdis 1, NASA and the European Space Agency, ESA, collaborated on a multi-telescope campaign, deploying every available instrument, from the Event Horizon Telescope to the Hubble Space Telescope. They needed one answer above all: was Charybdis 1 truly a black hole, or is it something else entirely? Meanwhile, theorists at the Institute for Advanced Study at Princeton proposed something even more radical. Charybdis 1 might be an entirely new cosmic entity, a gravitational bubble. If true, this would mean that black holes weren't singularities at all, but instead hollow cosmic structures with a core governed by quantum fluctuations. Could this be the key to unlocking the long-sought theory of everything, the missing link between quantum mechanics and general relativity? As JWST continued its observations, something unexpected happened. A distortion appeared near Charybdis 1. At first, astronomers thought it was a lensing effect, but further analysis suggested something more profound: a space-time rupture. The region around the forming black hole exhibited properties similar to wormholes, a theoretical bridge between different points in space-time. Could Charybdis 1 be forming not just a black hole, but a gateway to another region of the universe? Dr. Patel and his team were stunned. If confirmed, this would provide the first observational proof that wormholes could exist in nature. Was Charybdis 1 the key to interstellar travel? The discovery of Charybdis 1 ignited fierce debate across the scientific community. Some saw it as confirmation of quantum gravity, while others believed it was evidence of extra dimensions. Meanwhile, a faction of physicists proposed a controversial theory. Charybdis 1 might not be a natural phenomenon at all. Instead, it could be an artificial black hole, the result of an advanced alien civilization manipulating gravity. Although highly speculative, this theory gained traction as more anomalies appeared around Charybdis 1. Could an advanced species have created this black hole? And if so, why? With the world scientific community fixated on Charybdis 1, new research projects were launched. Project Horizon, a multinational effort to model black hole formation using quantum simulations. The Charybdis Array, a proposed network of deep space telescopes designed to observe high-energy cosmic events in real time. The Quantum Singularity Initiative, a collaborative effort between physicists and quantum theorists to redefine black hole physics. Meanwhile, the James Webb Space Telescope prepared for its next mission, aiming its powerful instruments at Charybdis, one to capture the deepest insights yet. Would it confirm the formation of a true singularity? Or would it reveal a new, unknown force in the universe? Months passed, and the event horizon of Charybdis, one finally stopped oscillating. It had reached stability. However, the data suggested something even stranger. Instead of a conventional Schwarzschild black hole, it seemed to resemble a Kerr-Newman singularity, a rapidly spinning, charged black hole. The gravitational waves emitted from Charybdis, one were still pulsing, hinting at unresolved physics beyond our understanding. The surrounding space showed anomalous energy signatures, suggesting the presence of an unknown quantum effect. Had Charybdis, one, truly stabilized? Or was it still in the process of becoming something else? The discovery of Charybdis, one, had changed everything. It forced scientists to redefine black holes, challenged the nature of space and time, and hinted at the possibility of wormholes, extra dimensions, and even artificial cosmic structures. As humanity prepared for the next phase of deep space exploration, one question remained. Was Charybdis, one, a doorway to something greater, or a warning of forces beyond our comprehension? One thing was certain. The universe was far stranger than we had ever imagined.